Okay, so in this video I want to talk about the wave function and how it arises from everything we've been doing. So what we've done so far is we've had our state vector, and ideally we've expanded it in terms of the eigenstates of the Hamiltonian operator. Because once we've done that, we can trivially solve the Schrödinger equation and find our state vector as a function of time. And this is the case for a two-dimensional system, so like our spin 1/2 particle. But we saw for more complicated systems, like a spin 1 particle would have three basis vectors. There's three, possible spin orientations. And then for a combination of two spin 1/2 particles, there were four basis vectors, and so on. And when we go to dealing with systems where we're talking about the positions of particles, generally what will happen is our vector spaces will become even bigger. Really, they'll become infinite most of the time. So that seems like an issue, but we can still we still would want to do what we did before. We still want to expand our state vector in terms of the eigenstates of the Hamiltonian. There will just be an infinite sum over these eigenstates. And typically when we, a standard notation, rather than labeling the eigenstates of the Hamiltonian by En, we just label it by n. And we would represent this, using our column vectors. And since there's an infinite number of coefficients, I need an infinitely long column vector, which doesn't seem very helpful. But luckily, it could be even worse. It can be actually even worse. So rather than having, so in this case, it's infinite, but it's, I guess the mathematical term is countably infinite. That is, you can label your basis vectors by integers. So n could be, 0, 1, 2, 3, and so on. But you could have a system where the eigenvectors, well, E can take on a continuum of values, basically. So I can't just sum. I have to change this sum. I have to make the transition from a discrete to a continuous system. So the sum becomes an integral. So conceptually, it's really the same thing. I'm just summing over my states. I'm writing my state vector as a linear combination of these basis vectors. It's just that I need to integrate because E can take on, it's a continuous variable basically. And again, I have my coefficient here that I've labeled by CE. And really, when you talk about, when things become a continuum, you just, rather than labeling, for each value of E, there's a CE. Well, really, this is just a function of E. And so I can represent my state vector as just this function. And obviously, that's maybe a better way of doing things than writing an infinite column vector. So even though these are infinite things, and that seems like a problem, it's really not. And in fact, since if we had our state vector expanded in terms of these bases, well, these are still the eigenstates of the Hamiltonian. So I can still easily solve my problem if our state vector is expanded in terms of these eigenstates. And of course, the problem is that most of the time we will not have our state vector expanded in terms of this basis. Normally, we have it expanded in terms of the position basis. And so for the position basis, well, when I measure the position of a particle, I can measure it to be anywhere. So it is also a continuously infinite vector space. So I need to write my state vector as an integral over these position eigenvectors. And again, position is a measurable quantity, so of course there's an operator corresponding to that quantity, and there are eigenstates of that operator. And we write the coefficients, again, as a function of the value of x. And this will be the wave function. And so it's completely analogous to the column vectors that we were working with before. So And just like the coefficients, so we know that the probability of measuring our state to be, or our system to be in the state, say E1, would be the modulus of C1 squared. So a similar kind of thing happens. The probability of measuring our particle to be at position, say x prime, will be the modulus of psi of x prime squared. And we have this dx here because this is really a probability density. So because we're dealing with, there's an infinite number of points the particle could be, the probability of it being at any one point is really an infinitesimal quantity. So normally what you say is the probability to measure the particle between, say, x1 and x2 is given by the integral of this quantity from x1 to x2. And that's just like, well, if I ask what is the probability of measuring my particle to be in either the state C1 or C2, well, I would just do the sum modulus of C1 squared plus modulus of C2 squared. So similarly here, rather than sum, I need to integrate from x1 to x2 to get the probability for the particle to be between x1 and x2. And yeah, so again, we'd work with our representation here, the wave function, and what we need to do is we'll have our state vector expanded in terms of the position eigenvectors basically, and have this representation here. And what we need to do is we need to write the eigenvectors. So normally we won't be working with this continuous energy spectrum. We will have an infinite discrete energy spectrum. So what we would want to do is find a way to relate these energy eigenvectors to our position eigenvectors. And so we know that we must be able to write these energy eigenvectors as some linear combination of these position eigenvectors. And for the nth, we'll say that for the nth eigenvector of our Hamiltonian, we write that as this linear combination here. Again, we have to integrate because position basis is continuous. And we'll call the coefficients phi of x. And so we'll represent our energy eigenstates by these functions, these phi functions. And so what will happen is, just like we represented when we were working with the representations for our finite dimensional systems, we had our state vector represented as a column vector, and we found that we could write this state vector, or our column vector, as a linear combination of basis column vectors. So, for our two-dimensional system, this basis vector, it would be represented by 1, 0, and this one would be 0, 1. And so you can write any 2D column vector as some linear combination of those two column vectors. So similarly here, we have our state vector psi of x, and we should be able to, our wave function psi of x, and we should be able to write that as some linear combination of these basis eigenfunctions. So basically, rather than working with column vectors, we have to work with functions now. And how do we actually find the eigenvectors of the Hamiltonian? How do we find these functions? Well, we need to solve this problem, which is exactly what we did before. To find the eigenfunctions, we need to solve this eigenvalue problem. And so when we did this in our discrete systems, we represented our Hamiltonian as a matrix, and then the problem of finding the eigenvalues and eigenvectors was diagonalizing this matrix, basically, or finding the eigenvalues and eigenvectors of this matrix. So what happens for these more complicated systems is this equation, rather than becoming a matrix equation, it becomes a differential equation. So our Hamiltonian, instead of becoming a matrix, it becomes a differential operator that acts on this phi. And so our eigenfunctions will be the functions that satisfy this differential equation. And so, again, that will lead to a lot of math and, fun, yay. But conceptually, it's really the same thing. Our goal is the same. We have this equation here. We want to solve it because we want to know the eigenvectors of the Hamiltonian, because once we've got that, we know we can write our state vector, or our wave function, as a linear combination of these eigenvectors. And once we've done that, we can trivially solve our problem.